Welcome to this last technical session of this first stage of our air quality community of practice. This is an initiative coordinated by WRI Mexico and Africa. My name is Ana Cecilia Perales, Air Quality Coordinator. This session is titled Use of Satellite Products to Identify and Quantify Emissions. The objective of this session is to assess satellite products to provide complementary information in order to know emissions, particularly in those places where this type of assessments are not carried out. Before we get started, Dr. Beatriz Cárdenas, Air Quality Director of WRI Mexico, will provide some introductory words. Please go ahead, Beatriz. Good morning, good afternoon, everyone.
Muchísimas gracias pues a todos quienes nos han estado
Thank you so much for
acompañando, quienes
joining
nos acompañan
today.
hoy. Hoy tenemos la séptima sesión, nuestra sesión de plática técnica, de seminario técnico, que es parte de esta comunidad de práctica de calidad del aire, que tenemos en este caso enfocado en participantes de Latinoamérica y que se expandió también para incluir a ciudades en África. Esto no termina una primera etapa de esta serie de sesiones, pero vamos a continuar con una segunda etapa, ahora también como parte del proyecto Canary Alert, donde haremos una evaluación de nuevo, haremos pararemos un poco en el camino y ver qué hemos aprendido, qué nos faltaría modificar. Bueno, recuerden que esta comunidad de práctica la hicimos primero identificando que había una necesidad, primero de compartir experiencias entre quienes están en diferentes ciudades, conocer qué están haciendo otras ciudades, tanto del hemisferio norte como del hemisferio sur, acercarnos a expertos que tienen trabajo y mucho conocimiento en los temas,
that
pero
are
también
quite
expertos que han
knowledgeable
estado trabajando en
about
las
these
ciudades
issues,
y que
and
también
also
queremos
experts
aprender
that
de
have
ellas y de
been
ellos.
studying cities,
Agradezco
and
en
we are
nombre de
very
todo el
interested in
equipo
learning from
que
them.
hemos estado
So
trabajando en
let
la
me
comunidad de
express my
práctica,
appreciation
no
to everyone who
solamente, por
has
supuesto, a todos los
participated in this
participantes
community of
de las
practice,
ciudades, de las diferentes instituciones,
particularly all of
y
those
en particular
participants
a
of the
todos
various
y
institutions.
todas los ponentes y expertos y expertas
Likewise,
que
thank you to all of the experts
generosamente
and
han
speakers
dado
who
su
very
tiempo, su
generously
conocimiento,
have provided
su
and
entusiasmo para
shared
compartir.
their time, knowledge,
Pues
and
bueno,
excitement around these
hacemos
issues.
un corte en esta primera etapa, pero estamos
So this will
listos
be
para iniciar una
a brief
segunda etapa.
ending of this
Será
first
muy
stage,
importante
and we will
conocer
be
sus
working on starting
experiencias,
stage
sus
number 2.
ideas,
It
sus
would be
opiniones, pues para poder
great to
iniciar la segunda
learn
etapa que
your
esperamos tener
experiences and
la primera
knowledge
de
that we
esta segunda
can
serie muy
bring
pronto.
them to
Como
the
dije
second
antes,
stage
esta comunidad de
shortly.
práctica trata de traer
As I
estos
said
temas,
before, this community of
identificar los
practice
temas,
aims to
traer
identify
expertos de todos
these
los
specific
sectores.
issues
Para eso
and
es muy
bring
importante saber
experts from
qué es lo que
various sectors.
necesitamos conocer,
That is
qué
why
es
it
lo
is
que
extremely important
necesitamos
to know and understand
compartir,
what is
y sobre
needed.
todo en dónde están
What do
las
we
áreas de
actually
oportunidad,
need to share?
pues sobre todo
Where
para
are those
mejorar
opportunities
nuestro
that we
conocimiento,
can
nuestra
work on in
generación de
order to
información,
strengthen
pues para lo que
our
todos y
data
todas
generation
estamos
and data
tratando de hacer,
understanding,
mejorar
which
el
is
aire que
what we are
respiramos.
all
Muchas
trying
gracias.
to do in terms of improving the air quality of our cities. Thank you. Thank you so much, Beatriz. We will start now with our presentations. We will start with Michel Grutter, researcher in the Institute of Atmospheric Sciences and Climate Change. He will be talking about advances in satellite monitoring for the characterization of air quality. And then we will hear from Benjamin Defoe from the St. Louis University, and he will be sharing information about high-resolution NO2 emissions mapping. And then Dr. Beatriz Cárdenas will host a Q&A session. And Yira Fonseca from the Modeling Center in Bogota. Now we will pass the floor to Dr. Michel Grutter. Okay, welcome everyone. First off, I'd like to thank the organizers of this event. Thank you very much, Ana Ceci and Beatriz Cárdenas. It is always a pleasure to share with you these spaces. I work in a laboratory in UNAM in order to provide data to the satellite missions so that we can collect more information and try to identify what are the challenges around the use of these new technologies and how to use satellite data. Okay, so let me start with that. I believe that this is a very important piece to remember so that we can review what are the benefits that we have of what we have learned in the whole community around satellite data. However, we also need to be aware of the challenges that the use of these technologies pose. The first of the advantages is quite clear, right? To be able to have a greater coverage of by use of these tools. It's quite evident advantage. And this is it's not about it being always continuous data transmission. It depends on the conditions of the atmosphere, and that is also quite a challenge that I will talk about in a minute. But advantage number two that I have here on this slide is the availability of having information where we didn't used to have data. And this is one of the big ones, one of the big advantages that we can obtain by the use of satellite tools. Number three is that depending on the shelf life of the satellite instrument, we can also make some air quality assessments and identify trends and variability factors, which would be quite complex to get if not by these satellite tools. So it is very important to keep them in good maintenance state throughout the years. From space, we can identify emissions and calculate the proportions. And also, since the instrument is in operation, it requires very little maintenance. It doesn't receive any kind of physical maintenance once it's operated. However, it does require a certain treatment in terms of signal and the data transmission mechanism. But in terms of the surface or the actual physical device, it doesn't require a lot of maintenance. And here's where the challenges come in. Of course, these are quite sophisticated means, both for the building of the instrumentation and the analysis of data, and that is what makes them so costly. A mission like these, in order to analyze air quality, only space agencies are probably the only ones able to afford this kind of tools. They are the only ones who can launch this type of satellites due to the high cost. However, there are some other initiatives for smaller satellites that provide other opportunities. However, one of the big challenges and the main focus of my presentation is the uncertainty. The satellite is measuring different types of surfaces in the same way, which is a big challenge because it's the radiation reflected from the sun that comes back to the satellite, and it needs to be analyzed separately. So we need to find in that data a number of premises in order to make an integrated assessment. And I'll talk about that later in my presentation. In order to differentiate, for example, a vertical column and a surface concentration, which is something that we need to take into account. And in many cases, the sensitivity of the instrument in the surface is not the ideal. So that is one of the big challenges in terms of really relying on the data coming from the satellite. There are certain factors that bring noise into the measurements, and there is an lack of knowledge of the measurement of the vertical, what we know, the vertical profile of the gas or the pollutant that we are trying to quantify. And of course, topography can have a negative impact in the certainty of the interpretations that we are deriving from that analysis. The next challenge is the big gaps that could be in the data due to the fact that there are no conditions to make this type of determinations. And in this case, for example, the capacity of detection from the satellite might be hindered. What the satellite observes is not necessarily an indication of what is actually on the surface. A clear example is the use of the optical density of aerosol, which is ever more used to calculate the fine particles PM 2.5 at the level of the surface. So there are certain conditions that need to be taken into account. And for that purpose, we need to understand more about the satellite determination in order to know how this is done. So one piece of what we are doing in our research group is the validation part. And the validation is not only about whether the measurements are right or wrong, but also when we are mounting infrastructure in order to do an equivalent measurement of what the satellite is actually doing from the surface, we will obtain a benefit, which is having data at various times in the day, which the satellite does not provide. Okay, so taking all of these considerations into account, we need to understand the processes so that it becomes clearer the difference between the column measurement versus the surface measurement. Now, let's remind everyone the difference between a polar orbit, which has a period of revisit in every part of the planet. It does a circumference twice a day, and it can see a specific part of the planet every several days. And it has a very wide coverage area. Most recent instruments could provide one visit a day, even at any point in the planet, which is, of course, amazing. But let's remind everyone that it's just one observation a day at the same time of the day. And we also have the geostationary orbits, where the satellite is observing the same part of the planet continuously. And this provides a lot of possibilities and opportunities. For example, we have the meteorological instruments and communication satellites, those buoys, but even today, we have not been able to use this type of instruments focused on the determination of pollution, for example. There is a mission called GEMS that was launched in Asia, and there are a couple of them planned for Africa, Tempo and Geocar, but they have not been launched yet. But this speaks to how technology is evolving towards having more information in a specific part of the planet, more available. Okay, so coming back to the definitions that I wanted to address, the differences between a surface concentration and a vertical column density. So with a specific instrument, we determine the number of molecules that there is in a specific volume. And this is given in micrograms per cubic centimeter, or what we know ppm, parts per million. Number of particles or molecules times the total number of molecules in that specific volume. And the vertical column density is the number of molecules in a specific area.
por ejemplo, de un instrumento viendo hacia el nadir.
So with a specific instrument, let's say looking in one direction, we have only a specific amount measured without knowing the vertical profile of that concentration, right? So if most of what we are measuring is closer to the surface, we are assuming that there's a volume where that specific amount is concentrated. So there is a difference here that we need to take into account when we do a comparison between what the satellite sees and what we measure in the surface. On the other hand, the fact that the atmosphere has a certain dynamic. So throughout the day, we have several layers, and when the sun comes out and heat comes, we have the planetary surface that is expanded or increases in height. So in some stable conditions, we would say that concentration would go down because it would have a greater volume in which that number of molecules is contained. On the other hand, if we are measuring a column and we have stable conditions, that means that there are no capture of emissions from the soil. The concentration of a column throughout the day as the expansion of the planetary layer happens shouldn't show that type of change. So this is a very big difference. So when we are analyzing satellite data, we are normally using information at one specific time in the day. We need to take that into account. And the dynamic conditions of the atmosphere not necessarily are the same one day to the next. So that is where, of course, several error factors come into play because that might not be the same surface that is reflecting back to the satellite, but also the dynamics in the atmosphere change day to day. So what we would normally do every time we design a satellite observation, we also need to design a validation strategy. That is to say, how can we use several surface measurements in order to validate our algorithms, which are indeed the responsible pieces to make the calculation. So there are several observation networks that we have that contribute to these improvements. Normally, we would do these validation exercises comparing with the measurements when the satellite comes with what the surface station is measuring in order to have a improved, enhanced knowledge of the error factors when we do a concentration map. And in a given case, we could also do the corresponding corrections in those cases where we know that it is clear that a correction is needed. So there are several satellite measurements that are focused on specific atmospheric bases or pollutants. From the NVSAT, which was in the 2000s, there were several missions focused on measuring how the concentration of these stratospheric factors close to the poles occur, which had a very important impact in what we know of what the ozone hole was growing in the year 2000s. This is just a list of some of the pollutants. There are so many more, but let me just focus on OMI because this is a mission that was launched in 2004, and we have been using it for so many years, 18 years worth of data now, which allows us to carry out some analysis in the longer term now. So if OMI is a satellite that was launched in 2004, it has a polar orbit, and it is designed with a CCD the two-dimensional detection component. It measures the wavelength, and it also measures a stripe of observation pixels that as the satellite goes through the planet, it does a sweep with this hyperspectral data collection through each pixel. And this satellite has been able to detect several atmospheric kinds or species that have been extremely useful. Another measurement that we have is the TROPOMI from the European Space Office from 2017. So we don't have that much information compared to the others, but it does have more spectral ranges. So it can also detect a greater number of atmospheric elements, and it also has a better satellite resolution. There are several studies that demonstrate the benefits that this new satellite platform has had compared to the others. And this is how technology evolves, correct? You learn from iteration. And this is just an example of the measurement of only one day from the TROPOMI instrument over the North American continent. And it opens the field of vision, and it can almost observe as a whole this part of the planet in only one day. And when we have yearly averages or monthly averages rather, we can see the information much clearer. We can see the emission sources much clearer. This is data coming directly from the TEMI's website, the KNMI from the Netherlands. And by April 2018, I did the same capture in East Asia, in China, just to compare how the detection of this particular pollutant is behaving in several parts of the planet. Okay, so now to improve our understanding of the measurements of the satellites, let's talk about the various detection techniques that are used. Every atmospheric component has a print, a particular fingerprint, if you will, or a detection wavelength. So they absorb radiation reflected by the Earth's surface in different sectors of the spectrum. So in this case, this is the ultraviolet visible spectrum, but there are some satellite instruments that have a detection range in the infrared, which is the case of carbon dioxide, for example, methane, or others. Therefore, a differential absorption technique known as DOAS use this type of satellites to do the measurement, and we also do those measurements from the surface. And this is just a photo to show what are those instruments that are set up on the surface to carry out the same type of observations that we also get from the satellite. So an instrument that is able to measure the comprehensive concentration as a column. So we have the FTIR, which is the infrared. We have the DOAS or max DOAS when it's a sweep. And the Pandora, which is also an UV instrument with various channels of observation. And besides doing those sweeps, it also observes the sun direct spectrum. So it looks at the sun and it measures solar radiation directly. And we also have other instruments on the right-hand side. We have 3 stations that have been set up in the center of Mexico. I will talk about where they are set up in a minute. And this is the instruments that are being installed in UNAM the National University of Mexico in the institute where I work, but we also have the observation center in the north side of the city. This is a map of the NO2 observation from OMI satellite. Likewise, this is a type of comparisons that we do, what we observe in the surface versus what the satellite measures. And here we have a good idea. We can have a better idea whether an over or underestimation is happening based on what we measure on the surface, but with a remote perception observation. So for formaldehyde, we are also doing certain comparisons between several instruments of measurements. Now, it is also very important to carry out this type of observations outside of the city. We have a station set up at 4,000 meters high in a mountain. This is the station that we have. It's called Alto Moni, and we have records since 2012. Likewise, looking into the hydrogen concentration or nitrogen concentration in order to detect likewise the transportation of pollutants coming from other regions. So this is the comparison of two types of observations across a day, a particular day, and this is the dispersion graph at the end. So this is the type of things that we are doing. We are generating this type of information and data in order to have a better understanding of how can we really rely on satellite measurements and how can it be used more responsibly. So we actually implemented several projects in order to understand the evolution of certain gases like ammonia. So this is a gas that is not very regulated or that has gathered a lot of attention, but we understand that it is a very important one because NH3 is is a gas that participates in aerosol. This is a gas that sticks to sulfate in terms of the secondary suspended particles. And this is a very important gas because when it is deposited, it also participate in the erosion of the soil. And as part of the sources, we know that mainly they are agriculture related for the introduction of fertilizers, residual water, composting, and of course, the motor vehicles, among others. So we have a project in order to detect the total concentration of ammonia on the specific observation points. And we also use the satellite YASI from the European Space Agency that measures the near infrared, and it detects ammonia among other gases. So this is how we put together what we measure in what specific point. This is an image of Mexico City where we are measuring ammonia with a minute by minute almost resolution, and the satellite measures once a day, as I said before. So we have the day variability by the surface measurement, but we also have the spatial distribution provided by the satellite. So all of that definitely enriches our studies because we might be able to do a validation in this case. So what the satellite is measuring compared to the surface measurements, and we can confirm whether the satellite is or not measuring what we see in that specific column. There might be an underestimation here, but we can also determine that the correlation is relatively acceptable. So we can know where the greater concentration of that gas is located. We know that in this case, it's not in the center of Mexico City, but rather to the northeast, where a big dump of trash and garbage is located, and also where water is distributed coming out from the city. However, there are other pollution sources coming from farms, which makes it also interesting in terms of study. We have also carried out wind trajectory assessment in order to know where the wind is coming and where it's going. So we know what are the sources coming from the city. And this is very related from pollution coming from dump sites, for example. And this is confirmed by satellite and by surface measurements. So we need to be quite vigilant around this type of activities because this is something that we may be able to reduce by, for example, having a residue management program. And now, recently, methane gas, CH4, has been gaining interest due to chemical residue. This is also the measurement of the satellite coming from the northeast side of Mexico City, where the greater concentration of this gas is located. And for that purpose, we have organized a certain number of detection programs to estimate the volume and concentration of this gas. We have in the southern part of a region closer to the airport, where there is a lot of methane emission for water treatment and dump sites as well, etc. And we detected in the measurement point here in the Xochiaca dump site that the concentrations that this instrument is detecting come from the north side of the city, northern side of the city. So with a simple model, a simple Gaussian model, we can do an estimate and compare it with the inventory. And this is the kind of things that can be done by linking all of these types of information sources so that we can have a clearer understanding of what's happening. These are just a few examples, but we need to learn how to use the benefit of high resolution of the measurement of the surface instruments versus the satellite measurement so that we can actually achieve the purposes that we want. And for that purpose, we know that we have the geostation orbit instruments. So these stations are designed to provide data throughout the day, which is something that we have been lacking. So we have TEMPO, tropospheric emission measurements of pollution. This is programmed to be launched at the beginning of next year. And it definitely is a instrument that will be very useful because the promise is that it will be providing data per hour. And this is a simulation of the type of data that this TEMPO satellite will be providing every hour. So this opens the possibility of using satellite data in a very important way for the regions that will be covered by that specific satellite. There is a similar mission that is planned for Europe and Northern Africa. And as I mentioned before, there is one that is already in operation in Asia. There is another mission. However, for the sake of time, I will not go in a lot of detail, but this one is much more focused in detecting CO2, methane, and greenhouse gas emissions in the American continent. Some of the strategies that we are proposing for the detection of these gases, not only in urban areas, but also in other areas that have very little anthropogenic emission concentration. We are planning to install one of these validation stations in the Yucatan Peninsula, which is an area that has a flat rainforest, and it's great for satellite validation. But not only that, it is also very useful to understand what is happening in this quote unquote healthy rainforest so that we can know the benefits of observation programs compared to carbon capture among others. So this is the type of things that we are working on in our working group. We always aim to keep up to date to the launches of satellites and enhancements, and also we are always looking how to contribute. Okay, so as a conclusion, I'd like to say that satellites generate extremely valuable information around spatial distribution of a great variety of atmospheric pollutants. Remote perception techniques are very useful to assess air quality, as well as the variability and trend of those pollutants, particularly in the regions where no information is available. That I hope is clear. And also the validation studies from the surface are needed, are necessary to improve the reliability of satellite products, because these instruments can have high uncertainty levels. And future missions will have a greater temporal and spatial resolution. And having said that, I would like to show my appreciation to all of the members of the working group, students, colleagues who have participated in this type of research, and also our funding sources by means of the products that we have launched in years past. And thank you so much, everyone, for listening to this presentation. Thank you, Dr. Grutter. Now the floor is for Benjamin Defoe. Thank you.
Good. So my name is Benjamin Defoe. I'm working at St. Louis University in Missouri, in the middle of the US. So I got started in atmospheric science really with the Mexico City project, working with Dora Cardenas and Michel, and looking at air pollution in Mexico. And then since then, I've looked at other things. You'll see some of the examples here. So I just want to say hello to everybody. Also want to remind everybody, I guess, thank you all who are working in air quality, and maybe we should remember to remind other people, the air quality remains a big killer, and it's something we need to work on, but it's also improved a lot for a lot of people. And so I think we need to remind people that the great progress we've made, and the great progress that we need to continue doing, and how a lot of people are living longer, healthier lives thanks to this work, even though it can be pretty invisible. So I know sometimes we feel like, oh, maybe it doesn't matter, but it does. It matters a lot. So today I want to show, I think, more in detail, sort of analysis of NO2 and CH4 emissions. I think you had really, now you can see from Michel's presentation that there's the whole work of people building the satellites and launching them. There's the whole work of people making retrievals and creating data products. And then there's the separate work of people who download this data and then analyze it. And I'm very much in that last group of people who are dependent on all these other people who've done this amazing stuff. But then I download the data and I do the analysis, and that's really going to be my focus today. So we saw this from before, but maybe ask yourself, how many weather satellites are there? Just in this picture, there's 25, and this is not a complete picture. We keep adding more and more. And then just also, we can see in comparison to what we saw in the previous presentation, here we have the geostationary satellites that are always above the same point, and so they provide continuous coverage during the day. None of these are, well, none of these in the West are air quality satellites. These are just weather satellites. So we have the South Koreans have an air quality satellite in geostationary orbit, and we're looking forward to TEMPO very much in order to get that kind of satellite. Up to now, a lot of the air quality satellites have been polar orbiting, and that's this little orbit over here, including the A train, a whole group of satellites that came right one after the other so they could see the same thing. And they sort of measure, they go over different parts of the globe every day, more or less at noon. So that's where we start. And then again, a slide similar to previous presentation. The air quality satellites will measure a swath as they go over. They sweep over the surface of the Earth, have a lot of pixels they measure. And for each pixel, they look at the spectral radiance and look at many different bands. And depending on the bands that they see, then we can create an estimate of the pollutant columns, not the concentrations, but the whole column between the satellite and the surface and the sun. So that's the background. And then we saw this slide, something similar to this slide. And all these different chemical components have different signatures in, this is looking just at the ultraviolet and visible range. They absorb at different wavelengths. And so I asked my students this, how many channels do we have in our eyes? We have 3 channels. We can see red, green, and blue. And our eyes make us think we can see millions of colors from these 3 channels that we have. But if we send a satellite up with hundreds of channels, then instead, in addition to seeing the colors, we can see concentrations, all these different components. So that's pretty wild to think about all the things we could see if only we had more channels. There are some birds actually have a 4th channel, and some even lobsters, I think, have even more channels. So, just perception, is both amazing and could be even greater. So that's kind of the science background there. I want to focus in today on the TROPOMI satellite, which has been in space about 4 or 5 years now. So we're beginning to build a decent record, a decent time series of pollutants. And it's able to see, as far as air quality is concerned, these 5 pollutants that we're interested in: ozone, formaldehyde, NO2, methane, and carbon monoxide. And really the species that it can measure the most reliably has been NO2. We get the clearest signal over the sources. That's been the best thing to look at. And then I'll show after that a little bit of methane, which is not that interesting from the air quality point of view, but is, of course, hugely interesting from the climate change point of view. So we have this kind of shift of interest. So let's dig right in and show you here a different part of the world. This is over Bangladesh, and we look at a map of NO2. So the smallest cells of NO2, the smallest feature that TROPOMI can see is about 3 by 7 kilometers, but we can oversample these to a fine grid, in this case a 3-kilometer grid, do a long-term average. In this case, I'm looking just at the non-monsoon period, the winter period, where it's clear skies, and so we have no obstructions. And we see a big NO2 enhancements over Dhaka. This is actually quite interesting because Dhaka and Calcutta are actually pretty similar cities. Dhaka is a little bigger than Calcutta, but they're not that different. And you can see that Calcutta has much less NO2. And so this is kind of striking. You can also see in India, there's a lot of pretty dirty coal, surface coal. These are coal areas, coal mining areas, and then big power plants next to the mines that have bigger NO2 signatures than Calcutta itself. So these are results that were published at the beginning of the year here in Environmental Research Letters. We were interested with the TROPOMI sensor because this is really the first time we can see detail at the urban level and even within the urban level. That satellites before, when they looked at NO2, would just see a big dome of pollutants without being able to see the differences. And so when we zoom in over here, over Dhaka, you can see it's not just a dome, there are features there of pollutants. The main thing actually that doesn't really jump out immediately from this, unless you're from Bangladesh and you know where the county boundaries are, which I don't know if anybody is from Bangladesh, but the city center here is in the middle and is not where the peak NO2 is, which is what we thought. We thought we would have most NO2 here. The peak is over here, and then there's this kind of funny little comma shape out here. So what we did is we used this method called flux divergence, which combines the columns with wind speed estimates to look at the changes in the columns as the wind flows over the city. And that way we're able to see not just the value of the column, but how much was added into that column as the air moved over the city. And when we do that, we get actually, with TROPOMI, we get a much nicer resolution of possible sources. So this is now where we're looking at this flux divergence, not just what the column is, but how much NO2 was added into that column as the wind went over the area. And what happens is you can still see Dhaka, the urban center, is not a big NO2 source according to this. The Narayanganj is this big heavy industry area. And this is where Google Maps is just amazing. You can go zoom in and you can see these big plants and you can see how they match the satellite columns. Gajipur is a power plant. Just a single power plant is responsible for this big hotspot there of emissions. Mauna is, there's really, it's light industry. So, a lot of garments, clothes are made there, but no big power plants or nothing. And yet there's a significant amount of NO2. Ashuganj is another power plant. So we see this detail come out from TROPOMI. And what we can do is if we match two-dimensional Gaussians to each one, then we can estimate what the actual sources are. And compare that then to the two official inventories. In this case, I'm comparing it to the Edgar emissions inventory. So this is what this next slide is going to show you. Now, this is everything in one go. So you can see it all and under a time pressure. I made this for the AGU conference. So on the top left, you have the initial columns. On that, there you see this kind of enhancement that varies by area within Dhaka. On the top right, you see the flux divergence that highlights separate areas. And then on the bottom left, you have these Gaussians that I matched to each hotspot to get an actual estimate of what the emissions are. And on the bottom right, then we compare our Gaussian estimates with the Edgar emission inventory. And you can see that there's kind of good news and bad news. I mean, there's clearly some estimates of emissions from the city. They're clearly there, the estimates from Narayanganj, from the heavy industry. The purple is heavy industry. But you see what's missing. Well, in Edgar, there's a lot of emissions from the energy sector, the light blue points here, which the satellite just doesn't see. Gorasal, Feni, Ashuganj are all different power plants, just tiny emissions in our estimates. And on the other hand, this Gajipur site that led to this huge NO2 source is absent in Edgar. And the Mauna industrial area, light industry area, is also just totally missing in Edgar. So we can see how TROPOMI's gotten to that point where we can now focus in on individual sources and then go check in the inventory and say, well, how important are these? And we can kind of develop both in a sense. One helps understand the other in both directions. So that's the summary of what we were doing for our project over South Asia. So I did want to, I know there are people from Africa on the call, so I did want to show some preliminary results here over East Africa. Doing the same thing, we take the TROPOMI over a long time period, we average it all on a very fine grid and look to see where the hotspots are. One thing that kind of shows up that is probably an artifact and to do with clouds and surface area and contamination of these enhancements over the rural area, although it may also be fires. I haven't looked into that. The other thing you see is you only see if you pay attention to the color bar. The color bar is totally different now. This is a maximum of 2.4 times 10 to the 15 molecules per centimeter squared, whereas before we had like up to 15 or 20 times 10 to the 15 molecules per centimeter squared over Asia. So the levels are much, much lower over Africa here than what we were seeing. So that's the other difference. But you can definitely see hotspots over the urban areas here: Dar es Salaam, Mombasa, Nairobi, Kampala. I know there's somebody from Rwanda on the call here, Kigali. There's also a little enhancement there. So if we focus in on those areas, then we can see, well, what are the sources that matter? And do we see those individual sources? We know there's a power plant here, this red dot where I have my pointer right here, there's a power plant. Whereas over here, this is just the urban area. And what is, I guess, was a little surprising to me was the power plant just does not show up very much compared to the urban area. So we see this kind of relative importance of different sources. That's Kampala. This is Nairobi. Again, looking at the flux divergence, not the columns. And here we see that there is a heavy industry sector here to the southeast around Hati River. I haven't visited yet, so I don't know. That shows up in the satellite, the main urban area here, but then also development along this highway here shows up in the satellite. I have to say we're limited with the satellite in what we can see, and it is sensitive to terrain and mountains and things. So you always have to bear in mind, sort of remember, what is it that the satellite sees? What can it not see, and how do we interpret it? And so we don't really know over here. This is probably to do with those terrain effects. So that's just to show you some of the things you can do with NO2 from TROPOMI at what we think of as a very high resolution from space. The TROPOMI also measures methane. And so I did something similar, which is to take the methane concentrations estimated from TROPOMI. This actually is different from NO2. NO2, it's columns, and here the algorithm is used to estimate the concentration of methane over different areas. And here I show just six different areas, and you can see clear enhancements over the whole urban area. I've added the cyan line is a line of higher population density. So it kind of shows you where the most people are living for each city, and there are different levels. So Lahore, a lot of methane, Delhi, a lot of methane. It's more distributed over Houston and Lagos and Madrid lower. I also added landfills. I know Mitchell was showing this something similar for Mexico and talking about methane emitted from trash collection. So the white diamonds here are where there are landfills. You can see from Buenos Aires, this is a massive land, really contributes to that part of the hotspot. But the hotspot in general covers the whole area, not just the landfill. Same thing for Lahore. Whereas in Madrid, most of the emissions do seem to be more closely aligned with the landfills. Houston's different because it has a lot of gas, oil and gas industry. So it doesn't seem to be getting its methane from oil and gas. It seems to be getting its methane from industry and different operations it has. The wild Texas there. The rest of the US kind of looks at in amazement. Bemusement maybe is the word. So this is the strength form. Methane from TROPOMI, and then if we zoom in, say on Dhaka with the methane, we see again, like we saw for the other cities, a big enhancement over the urban area of methane of Dhaka itself. And if we compare that to what's in the emission inventory for EDGAR, and we have these spots of emissions, EDGAR thinks that methane in Bangladesh is mostly emitted from fossil fuel operations, mainly gas production and power plants, the energy sector. And just comparing this picture over here on the top right with the picture on the top left, you can see there's a big mismatch. We are not seeing hotspots of methane where the power plants are. We're seeing methane very clearly where the urban area is. So that tells us that in EDGAR, we've got a totally wrong picture of what's happening. And this matters, obviously, because for climate change, what we really want to do is reduce methane emissions. This is one of the things that most countries of the world actually agreed to at the Glasgow conference about a year ago, is to reduce methane. So we need to know where this methane is. And TROPOMI then is this very valuable tool to tell us, well, this is where the methane is. You can't reduce something if you're looking at the wrong thing. So I did something similar with to the NO2, where we match a Gaussian shape to the methane hotspot, and you can see it's a pretty decent match. I mean, it really kind of matches this. This is the measurements here on the left, and on the right you have the Gaussian fit. And once you have a Gaussian fit, then you can estimate your emissions. And so we did this for a whole bunch of different cities around the world. Here, this is the map, the summary map with emissions. And we actually get much higher values than were reported in the previous presentation here. There's Mexico, city here in the hundreds of kilotons per year. Dhaka, it was kind of fortuitous for our study that we started with the worst offenders, so that helped us get us on the way here, but up to like 1,000 kilotons per year of methane. A lot of emissions, all northern India and Pakistan. And then also we Americans here are quite polluting per capita. These are all values. At the bottom, it shows you per capita. Whereas the size of the circle is the overall emissions. So I think that was, I want to show you sort of examples of detection at the urban level of both NO2 and methane. The conclusions from this, that, you know, TROPOMI's really got to that point where we can get very useful information at the urban level, at the point source level, and we can go and compare point by point with the EDGAR emission inventory. And obviously this will be even better once tempo is in the air, but it always takes a little while to then generate enough data to then do the analysis. We see that, you know, estimating emissions is hard. People here are probably involved in that effort. It's hard work. So this is not to discredit all the hard work. This is to say, you know, it's an ongoing process of improving the emission inventories. It's kind of never finished. And especially it improves as pollutant emissions are reduced. It becomes, you know, a never bigger search to find the correct emissions. So the satellites can help guide that. And then these sources of methane, which up to now people have focused on oil and gas operations, on the energy sector, maybe on landfills, but maybe not as much on just coming out from ordinary cities and what are the actual mechanisms producing that methane. We should really be identifying those in order to be able to reduce those emissions for climate change. So thank you for your attention. Be happy to take any questions.
And now we are going to have a question and answer section. Dr. Betty will moderate this section.
Pues de nuevo un agradecimiento a Michel y a Benjamin por sus excelentes presentaciones. Creo que nos dieron un excelente panorama de qué es la percepción remota y particularmente los productos satelitales y muchos ejemplos de cómo pueden ser utilizados. Y pues sí, yo me uno a la felicitación y agradecimiento que Ben mencionó con respecto a quienes seguimos trabajando en calidad del aire y particularmente quienes nos acompañan de todas estas ciudades, lo importante que es el trabajo. A veces coincido, su trabajo no es visibilizado ni reconocido, pero en efecto hemos visto en muchas ciudades del mundo una mejora en la calidad del aire con sus, por supuesto, con muchas mejoras en la calidad de vida de las personas. Tenemos todavía mucho trabajo, entonces pues, bueno, agradezco también el trabajo de Benjamin y de Michel, que siguen trabajando en estos temas. Ya Benjamin se acordaba que coincidimos también hace muchos años en el trabajo de la Ciudad de México, de la zona metropolitana. Bueno, gracias a que continúa ese trabajo en la Ciudad de México, en la zona metropolitana y en muchas ciudades del mundo, es que en efecto tenemos muchas mejores condiciones y todavía nos faltan. Empezaría preguntándoles, hemos visto cada vez más el uso de estas herramientas, de los productos satelitales, ya lo decía Michel, desde esta calibración o de esta comparación con mediciones de superficie. Benjamin también hablando también de todo el trabajo que se hace cuando se bajan estos datos y se analizan. Y bueno, como esto, ustedes ya lo mencionaron, ¿no? Como bien nos ha permitido identificar fuentes que antes no se podían identificar también con la herramienta que tenemos, que es inventario de emisión. Yo les preguntaría si nos pudieran dar 2 o 3 sugerencias, sabiendo que tenemos a muchos de los posibles usuarios o ya usuarios de estas herramientas. Ya el doctor Michel hablaba de tener algunas consideraciones, por ejemplo, cuando utilizamos un producto satelital como el AOD para cuantificar emisiones, concentraciones en superficie.
concentrations in the
¿Ustedes
surface.
tendrían algunas
So,
sugerencias
do you
en
have any
general
suggestions in
de
general
cómo
terms
empezar a
about
utilizar estos productos
how to
satelitales
start using
para
these satellite
identificar aquellas
products to
fuentes
identify
o
sources
determinar concentraciones en
or
superficie?
to
¿Cuáles serían como
determine
las
surface
principales
concentrations? What are the
sugerencias
main
de cómo poder
suggestions
utilizar
that
estos
you would have
productos
about this,
y
about how to
sabiendo
use these
también todas
products,
las
taking
sensibilidades o
into
los
account
artefactos? A lo mejor es
all of
una
the
pregunta un poco
artifacts and
general,
everything?
pero
Maybe it's too broad of a question, but go ahead. Okay, so thank you for your question, Betty. There is a recommendation that I would like to do. So clearly, sometimes it depends on the budget that each country or region may have. This can limit what you can implement, but based on my own experience using data from different sources, I think there is a large benefit to combining a lot of sources of information when we do not just focus on one single source of data. We can see that not just in regions where they don't have surface stations and they base a lot of their conclusions or a lot of their analyses or characterization on the region based only on satellite data. So the same thing happens with a global trend that we are seeing right now with the low-cost sensors. And I think that it's very important to not ignore surface level monitoring stations. We shouldn't ignore them. Clearly, they are very expensive. They're also expensive to maintain. However, it is important to use them to understand what is happening in a particular region and to be able to compare this information. So many times I would say, if we're going to implement a network of low-cost sensors, at least one well set up station that has the certified analysis capabilities for measuring air quality is important, because then that enables you to understand the differences, it allows you to apply the necessary corrections, and the same goes for satellite data. If we better understand how a satellite is detecting emissions from a region and we can compare it with surface data, then we can broaden the scope of our knowledge. We can better understand what's going on. So that is one of the recommendations I have. Do not forego surface data, especially when it comes to regulation, actually. It's clear that, I mean, as much as these technologies advance, whether it's satellites or micro sensors, they're still not at the level where we can make decisions at the level of air quality management. They do help us, they're helpful, they're informative, but they still cannot be used for regulation.
I agree totally with this question of the reference methods, and having a reference site is really very important. I know for the South Asia work, we benefited from the network from the US Department of State that had measurements at the embassies that we can use as a reference for other types of measurements, including satellite measurements. And I would add also the importance of making things visible. That, part of the problem with air quality is we can't see it. If we could see the insides of our lungs, there would be fewer smokers in the world, so that if you could make it visible. And what this does is both the satellites, the low-cost sensor networks, the reference methods, they make the invisible visible. And so I think to start off with, there's quite a few tools to handle the satellite data and make pictures or download pictures to sort of show people, oh, this is how it is. But that's one part of it. But then I think also then the regulatory piece, you still need actual measurements on the ground to sort of say to people, look, it's, these are the trends, And you want to encourage people too. I mean, a lot of places are getting better. Say, look, these are getting better, but not always. So.
Thank you so much.
Que a veces tenemos que tener todos en cuenta, a veces nos vamos con estas nuevas herramientas y creemos que podemos poner todo en eso. Creo que lo que ustedes dicen es esta combinación de datos y definitivamente no olvidarnos de los datos de referencia, sobre todo para en términos regulatorios y sobre todo pues dar información sobre a la población, ¿no? Y en efecto, todas estas herramientas nos ayudan a hacer visibles todas estas fuentes de emisión invisibles. Nosotros les llamamos source awareness, esta identificación de fuentes, qué es lo que genera o que provoca la calidad del aire en nuestra ciudad, ¿no? Que a veces vemos y a veces no vemos. Un par de preguntas
a couple of questions in the chat. The first one.
Bueno, preguntan cuál es la resolución espacial del modelo de Nairobi. Y bueno, Benjamin, creo que no es a lo mejor, bueno, si tú puedes comentar. No es el modelo, es la medición.
It's not the model, it's the...
What I showed is column measurements from TROPOMI. And the TROPOMI cells, now they're down to 3 by 5 kilometers? It changed a little bit. So then I oversample them to a 1 by 1 kilometer cell, but the root data is still 3 by 3 kilometers. And then depending on the types of sources, you can see more or less resolution. But that's the...
Thank you, Benjamin. The other question
¿Cuáles son las causas que consideras que son,
what do you think are the causes,
que son las causas por las grandes emisiones o las fuentes de las grandes emisiones de metano en Dhaka?
Methane emissions in Dhaka.
I'm hoping to be able to have more information on that. So we're not, so Jamie Shower and I were working on this together, and we're not really methane people. We're really kind of air quality people, sort of looking a little bit, you know, in the data, just always trying to see what's in the data. And what we saw across the world is there's a correlation between how much methane was emitted and how much sewage went untreated wastewater. So this is still very new, but we're thinking it's related to sewage. And we're not thinking, I mean, some of it will be related to natural gas usage. Yeah, it's still very much an open research question.
Metano, pero se ha trabajado en calidad del aire. Creo que lo que hemos visto, y bueno, ustedes, en particular ustedes dos han estado en este vínculo de calidad del aire y ahora en esta integración de cambio climático. Parte de los temas que hemos tratado de ver en esta comunidad de práctica es justamente cómo hacer un manejo de la calidad del aire o de nuestra atmósfera en las ciudades de una manera más integrada. Y pues solamente un comentario, ¿cómo ven ustedes que ahora teniendo más herramientas para identificar estas diferentes fuentes de emisión que nos preocupaban por calidad del aire, pero que ahora también sabemos que es una importancia muy importante en cambio climático?
Now we know how it affects climate change and how important it is. So do you have any suggestions about how to see these sources of quantification of sources that affect air quality, but also thinking about the fact that they have implications for climate change? Well, one of the things that we have understood and maybe it would be worthwhile to raise awareness in people about this is that there's a very important relationship between air quality, you know, the air that we breathe, with the gases that we are emitting and that impact the climate, of course. The sources are completely related. So it's about energy consumption, and a lot of the efforts that communities have to undertake is to reduce emissions. And this is both going to yield a benefit in air quality and also in terms of the planet's climate. And, well, this is a message that little by little is being understood by society. And as scientists, we need to continue with this flag, saying that, yes, it's about curbing emissions, but not just for someone's benefit, but for the benefit of all, and these two causes. So I think that up to a certain point, this is being achieved, but there's still a lot of work to be done.
Yeah, I think I agree. I mean, and to look for co-benefits, look for things that can be done together. And that's true even outside of air quality and climate change. I mean, like traffic jams are a problem. What can we do to improve things across the board? So really to be looking for co-benefits, things that benefit on multiple dimensions and that can help everybody.
Well, thank you very much. We will continue. Thank you, Michel. Thank you, Benjamin.
Now we will go on to talk about local experiences. This session will be shared by Yira. Thank you very much, Yira, for joining us today. Hello, everybody. Good morning. Good afternoon. So, I'm from the CMAP at Bogota. We're going to talk about some experiences that we've had based on the GOES 16 in RGB, fake color, which was used to analyze some data coming from the city of Bogota. So first of all, I'd like to speak about the context a little bit. So I think the project is based on the fact that we want to have an operational satellite system for the Ministry of the Environment. And so we're starting with this project by analyzing regional pollutants in the city of Bogota. This project has a scope of 5 years, over which we have a lot of objectives. First, in general, looking at the possibilities of analyzing dust and other pollutants via satellite, verify the degree of usefulness that these satellite products can offer with all of their characteristics, also look at the rooms for improvement, and also look at how some methodologies can allow to validate the use of satellite information to infer surface concentrations in Bogota. So this project has 4 stages spanning 5 years. First, particulate material analysis. The second is oriented to gas. Then we intend to work with different environmental applications based on satellite data, and finally, to establish an operational system for the Ministry of the Environment. In this presentation, we're going to go over the first stage, which has to do with particles. So 3 steps. First, we're going to explain how we obtained this product. We made a comparative analysis of this product with the surface level concentrations as they were measured, and a couple of case studies that were considered also. So the RGB product proposed is based on an algorithm proposed by GeoNetcast Americas in 2018 that includes an analysis based on ABI, the 4 bands for the ABI. And then we have an RGB composition, and this can help us highlight some of the specific characteristics of these bands. And then we can use colors to highlight the dust and other certain elements. So we work in an Anaconda environment in Python, and it was a 15-minute scale. As you can see here in Amazon, we built a general mass scale script, and then we started building the product like the one you can see here on the right-hand side of the screen. This product has the RGB composition. It was known as fake RGB color, and it had temporary series based on several graphic analyses to analyze the climatology based on an annual cycle for these characteristics, another monthly cycle, and a daily cycle as well. So we're going to work on the bands separately to compose the fake RGB colors that you can see here. So we did this for 3 stations, or rather 13 stations, sorry. And it was available from January 2018, and then we tried to maintain the same cycle of seasons that were operating at the surface level. So we did this analysis, and we tried to analyze based on an annual cycle for the RGB. And so we divided it in 3 bands. The first is red, that would show us that in the annual analysis, there was a trend. This color was trending to increase in the middle of the year. But if we compare this value with the particle material stations, it doesn't regularly match. That is to say, this composition in the color red does not necessarily allow me to see clearly what the characteristics of the particulate material are at the surface. And this trend of increases at the middle of the year, we see this in the 4 years that we looked into. We can look at it cumulatively or separately for every year for each season. Now, as for green, we noticed a trend that was a little bit more similar to what we saw at the surface level stations for the particulate materials. So it was trending more to the second half of the year, but it was a bimodal trend. So we can see each of the green bands for each of the stations, but it still doesn't appear to be a great indicator of the behavior. It doesn't really track the behavior of the dust. But we found that for the annual comparisons, the blue cycle has a tendency to be very similar to the concentrations of particulate matter. And this made a lot of sense, logical, but it was also interesting to see how this tracked. The concentrations were almost exact based on the trend for particulate matter at the surface level. And this apparently provides a better explanation of these concentrations. At the monthly level, by analyzing the daily cycle quarterly for each season, we would see that we have a typical distribution of particulate matter at the surface level. These are the lines that you can see in this graph here. But red showed a trend to, it was decreasing around noon. Green showed an increase in the same time frame, and blue an even more acute increase than green. So apparently there is a trend, a specific behavior that differs a lot from the surface level behavior. So we are not necessarily responding properly to the characteristics seen at the surface level. So then based on this, we moved on to some general case studies to verify the maximum concentrations for the 4-year period daily. We compared it for each month, and we found that in June, in 2020 specifically, there was a particular case. And here are some of the graphs for other months, and we can see how concentrations can vary at the surface level for each of the 4 years that we considered, but there's not quite a peak like this one. And for June, we saw that all of the stations perceived this, and we thought that it was an important thing to consider because we were in the middle of the pandemic and there were strict restrictions on transportation and other activities. So if this was an analysis of transportation, it made sense to take this as a case study. It was important to do that. So what we found is that the trends for concentrations in these dates in particular, this would show that in these hours, blue would decrease importantly during this range of days or hours. So for this, we considered a range between 20 and 26 of June 2020. And as for red and green, the values would oscillate, that would vary. But there was an increase that was not as marked, but certainly a trend. And comparing the cases for greater concentration for the days that we analyzed, so in black, we can see the bars for the particulate matter, yellow is 2.5. So for this case in particular, the response of the satellite data was variable across the days. It wasn't that determining, but we did see that in the cycles of greater concentration or greater accumulation when the concentration increased, blue was always below, and it was always noticeable. However, when we verified this information, we noticed something that was not taken into account during the first analysis, which is that the dust values that we see in the satellite, based on the RGB composition, it includes a lot of information classes, but only the colors related to magenta would correspond to dust. So some of the colors could be dust, but others could be water, could be some features of the desert landscape, things like that. So given these conditions, we decided to filter the images, the RGB images, using the ranges corresponding to magenta. So we created these clean dust images, as we call them, and here are some of the images that we considered for this. A lot of the information evidenced by the RGB concentration and the fake color correspond to water vapor or other substances that really weren't interesting for us, but there was the presence of some important masses of dust that matched what we were looking for. So, for example, we could see a lot of these masses and some of the ranges in concentrations that we considered light or moderate, and that came in from the east and from the north of the country. So apparently this clean quote-unquote study can let you see in more detail what is actually going on in this area and in this city. So sometimes we don't know how the surface level concentrations relate to the RGB records taken by the satellite. So we had a very strict filter. We took as a second case study the clean case study, where we identified where the monitoring stations would match the RGB range that we considered for dust. So only 2 records or only 2 days fulfilled our characteristics, and we verified when these conditions took place. And we found that for most of the stations, when there was an increase in the surface level measurements for particulate matter, 2.5, we could see a notorious decrease in blue band colors and a more varied increase, oscillating increase in red. So the fall in the blue values shows that the satellite can pick up an important relationship between the surface level concentrations and the values in mainly the blue band. And this analysis or this exercise, well, we have a lot of variation in these concentrations, but we can see this in all of the stations. So when we look at the RGB ranges, apparently in almost all cases, I mean, it appears to apply for all. And the cases that we managed to analyze, we could see the records for the surface level concentrations and the RGB, and we always saw that blue would decrease and red would spike. So we concluded for now, because we still have a lot of work to do, but that they're an available series. This is a time limit, of course, because we can't have robust analysis and provide more variable conclusions with lower uncertainty because of the time frame. But this is still a valuable series because we can provide information on the hourly basis, and we have an area of 2 kilometers. And we also presented an interesting analysis that we haven't verified yet, that there is a composition of RGB with specific seasonality for the city, verified in the 4 years of study. Some match the particulate matter, like with blue, others do not, but it's a seasonality that we had not observed before. We didn't have a specific analysis for the city. At the daily scale, we saw that there's a variable cycle in RGB that doesn't correspond with the cycles in the monitoring stations, which shows that even though satellite data is useful for measuring transportation and certain atmospheric conditions, it's not a direct way of measuring local emissions. And the high concentrations associated with transportation have a very clear trend for decreasing blue bands and a less clear but quite noticeable increase in green and red especially. Red is quite variable, but it does show a trend to increase when there is increased concentration. And for the 2020 case study, this work allows us to see that RGB in a way, allows us to understand in large measure how the particulate matter behaves. And finally, I'd like to talk about some of the next steps. We tend to operationalize the information so that we can work sequentially and verify if what we have found will occur regularly. The idea is also to try to analyze the RGB for clean dust case studies because we have a lot of unverified information also related to fires and some events or cases of contamination associated with transportation. And finally, a couple of possibilities, exploring the methodologies for inference in the surface, for the concentration of particulate matter, and also exploring the possibility of using this information to later on analyze black carbon. And thank you for your attention. Thank you, Yira. We hope that you can be with us in the next event, the South-South Dialogue. This will be the closing event for this first phase, and we will be sharing more details with you through our traditional communication channels. And well, thank you very much. I'd like to thank our panelists. I'd like to thank all of our attendees for being here and for your questions. Thank you, everybody.